Okay, so off we go. Today is our last day of Chapter 7. We actually already kind of finished the new material. Technically, I've already shown you everything, all the new ideas, right? What I want to do today is kind of bring it all together and show you how the ideas all fit together. And then we're going to do a bunch of examples, right? The point of the examples being not, how do the ideas work, but how do you take a question and then do what I like to call diagnose and identify, wait a minute, is this a Stokes' theorem question, or is this a path independence question, or what are we doing here, right? Okay, so anyway, let's dive in. So in the notes, I have this entered on our next page. And again, this is just my sort of short and compact version of what's actually, I think, really a better thing here is this sort of the full-sized diagram that I have. Again, it's available on the website, download. It's called diagram.pdf. It's in the class materials folder, if I remember correctly. And I've already done some of this, but I want to repeat it because I think it's really important. I want to make sure everybody's comfortable with all this. So again, the very many patterns that there are that you can see, patterns and relationships and connections, and it's just all sorts of good stuff in how this diagram is organized. By the way, again, not in the book, right? This is something I kind of created by boiling off formalities off of much more sophisticated constructions that we can't talk about. Okay, so let's talk about the fundamental theorem of line integrals. And the fundamental theorem of line integrals basically says that if you have, let me circle it here, that theorem is saying that if you take a function and push it forward on the diagram, if you take a curve and push it back on the diagram like this, then this evaluation of that function on those 2 points, this evaluation, line integral of this gradient vector field over our original curve, you get the same thing either way, right? And of course, I like to abbreviate this. Sort of the shortened version is something I like to just draw like that. It's just a little bit easier to kind of write down. So we've already made this observation, but let's go ahead and make the final sort of observations of the strength of the analogy with these other theorems. And that is, I claim that this pattern is exactly the pattern that holds for Gauss's divergence theorem. It's the exact same pattern. Now, it's elsewhere in the diagram, or said differently, it's about a completely different geometry. It's three-dimensional solid regions, and they're two-dimensional boundary surfaces. Yeah, right, totally different geometry, right? But in the diagram, how the pattern plays out is really morally the same. Likewise, Stokes' curl theorem. It's the same pattern. Different geometry, different dimensions, blah, blah, blah. Of course, but the same pattern on the diagram, right? So one of the advantages of this is that if you're trying to understand, as you are, trying to understand all of these ideas, if you just sort of view these theorems as independent and disconnected and unrelated, then you've got three entire separate theorems to learn and no way to sort of pare that down. But if you think about them on the context of this diagram, it's just one pattern, not three separate theorems. Right? So I think there's a lot of value in that. And I encourage you to try to understand those theorems, again, on the pattern of this diagram. And by the way, for 2 dimensions, morally equivalent diagram up here, Green's theorem says that if you compute Green's operator of a vector field, take the boundary of a 2-dimensional region, then that boundary line integral and double integral of Green's operator, same thing. So again, same pattern, right? So arguably, depending on how you look at it, maybe you might say there are 5 of the same pattern, right, on these 2 diagrams. Okay. All right. Here is another observation. Let's go back to the 3-dimensional diagram. Let's see here. We've talked about, back in Chapter 3, I talked about lifetime theorems. I don't know if y'all remember that. That was just an idea I kind of threw at you. Metaphor for a general truth. And then there was recently we talked about local tests. They also fit very nicely on the diagram. Now, I wrote a version of them down here. That's all of this business. Case could be made that's more sort of clunky than it is helpful. But anyway, the idea of the way I've written this is that the solid lines represent the hypothesis. In other words, if this is true, and then the dotted lines represent the conclusion, then this is true. So this first line right here says, if you have a vector field that's the gradient of a function, then the conclusion is that the curl of that vector field must be 0. Right? And so anyway, all of the lifetime theorems are, in fact, looking at us right here. If you want to decide whether a vector field is or is not a gradient, take the curl. Right? If you want to decide if a vector field is or is not a curl, take the divergence. Right? And these are theorems that we've talked about, in the last few days. And again, they play very nicely together on the diagram. So again, a nice little advantage of organizing things in this way. In particular, you look at these operators right here. And this is, by the way, the one thing that you do have to just rote memorize. Right, is which operator goes where. And I think if you play with this diagram enough, you'll find yourself having a hard time not remembering that, right? Because it's just 3 things, and you just have to remember which ones go where, and that's kind of all. Right? Okay. All right, now remember also, we talked about certain special vector fields. And I emphasize, these are special vector fields. Not every vector field has these properties, but there are special vector fields that fit with the following 3 properties. Any regularity aside, any vector field that satisfies any one of these properties also gives you the other 2. Namely, we're talking about gradients. Gradient fields are special. By the way, another way to say it, a gradient field is a vector field that has an anti-gradient, right? In other words, where you can sort of go backwards through the gradient vector, the gradient arrow, to get a function whose gradient is your original vector field. So another way to say it. Okay, special vector fields, gradients, also have the property that curl is 0. Right, we talked about that. That's, again, kind of our lifetime theorem, aka local test. And then they also have this property called path independence, namely if you were to take 2 curves and if they have the exact same boundary points, then you get the same value for the line integral. Okay, so we've talked about this little, pattern sort of way to represent these 3 different properties of the same collection of vector fields. Again, regularity issues aside. So let me add to that a little bit. How did we conclude a relationship between being a gradient and being path independent? And you may recall we used the fundamental theorem of line integrals to draw that connection. Yeah. Anyway, it's just, in fact, I think this ends up looking a little cluttered. Let me do it like this. We use the fundamental theorem of line integrals to draw the connection between being a gradient and having this path independence property. Okay. We also, now just a reminder, we drew a relationship between path independence and curl being 0. And if you look back at how we did that, Stokes' curl theorem was the big tool that made that happen. Okay, so now again, we've got a sort of a little pattern that we've put together. Not clear why we care about this or what's to be gained from this, right? But here's what it is. This pattern about our special vector fields, the properties they hold, how we see the relationships between those properties that they hold, that entire thing, you can just slide it on over. We have special vector fields that are curls, namely for which divergence is 0, namely that are surface independent, right? Powerful ideas, right? How did we find a connection between being a curl and being surface independent? We use Stokes' curl theorem, right? So not only does the pattern of conclusions hold, the pattern of reasoning holds, right? In the same way that the fundamental theorem of line integrals related to path independence and being a gradient, Stokes' theorem relates being a curl and being surface independent. And to me, this is just a huge jaw dropper. And by the way, recall as well, we've already made this observation that Stokes' theorem was how we related irrotationality to path independence, and continuing in the pattern, the divergence theorem was the primary tool that we used to relate divergence being 0 with surface independence. And you can look back through the notes and find these arguments that we made. But this very, very, I hope, persuasively strong pattern shows that you can use your understanding of what's going on in one of these contexts, right? If you feel like you have a good understanding of path independence and all the arguments related to path independence, use the pattern, right? And let that tell you, let that basically do the thinking for you in some sense, which tools you'll need to draw which conclusions. So really, really powerful idea there. Okay, let me pause real quick before we go on to the next thing. Who's got a question? Yes.
A question for the fundamental theorem of line intervals. To make that equation, the fxb minus fxa.
Yep.
The line has to be path independent. Right?
Yes, it does. And let me walk through the diagrammatic sort of rationale there. So you're right that we need this path independence idea, right? And the reason we need that path independence idea is because that's always simultaneous with being a gradient, which is simultaneous with having an anti-gradient. And of course, the anti-gradient here is the thing that we're going to be plugging into. Yeah, so absolutely. Does that make sense?
Yeah.
Exactly. Okay. Alrighty. So now y'all have probably seen in the notes, and I'm going to switch over to back to the notes page again now. And we've already kind of talked through all this stuff. And we're going to get now into diagnosis. So when you look on an exam, and by the way, of course, y'all have access to bazillions of my old exams. Keep in mind, my old Math212 exams are perfectly appropriate study material, right? The course Math212, the course Math219, they're practically identical topics covered. Slightly different take, because y'all have a linear algebra background, and that frees me up to talk about linear transformations and certain nice tools, right? But as far as the content covered, they're identical. So you have coming on 20 years worth of old Math212 exams that you can look at. And when you see questions, for example, like this, where there's some givens, and then the question is to compute a line integral or compute a flux integral or whatever it might be, there is a great way to use the diagram to diagnose what you should do, or at least to help you think through what you should do, right? Obviously, it can't literally do the thinking for you, right? Okay, so here is the first step in the process. I say context from the diagram. So what I mean is, look at your diagram. Oh, and let me get back to... Yeah, there we go. Look at your diagram and ask yourself, wait a minute, where am I? And by the way, for which diagram? Am I looking at the two-dimensional diagram or the three-dimensional diagram? So back to the question. This first question, I see that the vector field has 3 coordinates. I see that my parametrized curve has 3 coordinates. I think we're in 3 dimensions here. Kind of has to be, right? So now that we've identified that the question that we're looking at is 3-dimensional, go back to the diagrams here, and don't even look at the 2-dimensional diagram. The 2-dimensional diagram doesn't apply, because we're not in 2 dimensions. We are in the more complicated case of being in 3 dimensions. And now furthermore, where on the three-dimensional diagram are we? Well, I've been asked to compute a line integral. So let's find on the diagram, where are the line integrals? Right? Well, here we go. Line integral right there. So that's what I'm looking at. That's where I'm looking at it. R3 diagram, line integrals, and a bunch of free information already available. Here are two theorems that conceivably might apply. There is no way that Gauss's divergence theorem is going to apply here. Gauss's divergence theorem doesn't even connect with line integrals. It doesn't have anything to do with line integrals. There's no chance that this is going to come up. Right? Does that make sense to everybody? Yeah. Okay, so not only should you not waste your time playing with Gauss's divergence theorem for a question about line integrals, you should make the very deliberate point of not even making it look like maybe you were thinking about it even a little bit, because it looks really confused. And you got to keep in mind, your goal when you're writing your responses on exams is to persuade the grader that you know what's going on, and that you understand ideas. And if you are computing divergence, or if you're writing down triple integrals for some reason, or if you're talking about Gauss this or that, or solid three-dimensional regions, anything along these lines, it makes it look like you don't understand how line integrals work. It also makes it look like you also don't understand how Gauss's divergence theorem works. Right? So again, it's a bad look. Right? And again, keep in mind the grader is going to be trying to assess from what you've written how well you understand the ideas. So avoid all this stuff like the plague on a question about line integrals. Does that make sense to everybody? Okay, so the diagram's doing us a favor. It's telling us what not to do in addition to what maybe to entertain possibly doing. Okay, now what else does the diagram tell us? The diagram does give us some more information. We supposed to compute a line integral. That means we're given a vector field and we're given a curve. And notice back on the why won't that? Oh, because I'm hitting the wrong thing. Back on the question, yeah, indeed, we were given a vector field and we were given a curve. Parametrized, whatever, we were given a curve. Okay, so what do we do? Well, the diagram basically tells us this vector field, the integrand, for the line integral you're trying to compute, what does the diagram say to do to these vector fields? Well, the operator that this plugs into is curl. The diagram is telling you, compute the curl. See what you get. The diagram is also telling you about this curve that you're looking at here, the curve over which you're computing this line integral. The diagram tells you exactly what to do. This curve is the input to the boundary operator. So look for the boundary. Think about, in other words, the endpoints, the start and end of the curve that you've been given. Take a look at those. There might be useful information there. Okay, so let's do it. Let's follow the instructions. Let's take this vector field right here and compute the curl. And I'm going to spare us the computational tedium, but make sure you can do that, right? And you're going to have to be able to crank this stuff out quickly. Turns out the curl is 0. So what does that tell me, right? How does that help me decide what we're doing? What does that help me to understand? The diagram points out, by way of the lifetime theorems, that because the curl is 0, there must be an antigradient. And that opens up the possibility that the fundamental theorem of line integrals is in play. That's an option. There is an antigradient, and therefore I can use the fundamental theorem of line integrals if I want to. Is everybody on board? See how the diagram's guiding us through the process, right? It's helping us diagnose and figure out what we're going to do about this thing. Okay. All right, now again, next thing it tells us to do, it's telling us right here, look at the boundary points of your curve. Okay, all right, noted. Let's look at the boundary points. So I'm going to take oh gosh. For this parametric curve, I'm going to take the starting value of t equals 0, plug it in, see what we get, and let's see here, we get t equals 0, we get 0, oh come on, that looks like a 6, 0, comma, 1, comma, 1. All right, now we got to look at the ending point. Let's take t equals 1, plug it in, and I get negative 1, comma, 1, comma, e squared. Okay, so I have found my boundary. My boundary is that this curve starts there, ends there. Quick side note, the way I did that here is because the curve came parameterized. It won't always come parameterized. It might come described in some sort of wordy geometric way, or it might come described by some equation or pair of equations, whatever, right? Who knows? However you have to, you might even have to resort to drawing a picture, right? But one way or another, you got to identify starting and ending points. Now back to the diagram. What does this tell us? Well, I got 2 different points. 2 is not 0. So that means there is no anti-boundary surface. If there were an anti-boundary surface, then I would have a lifetime of 3, and again, that doesn't happen. That's not a thing. So therefore, there can't be any surface to talk about. Is that good? Everybody see how I kind of did that? Pretty sweet. By the way, if you don't like the lifetime idea for the geometry case I'm making here, just think about some curve. If you have a curve that starts here and ends up over here, that means it didn't close up, right? And if it didn't close up, then it doesn't enclose any region, right? Said differently, if you make a fence and it starts over here and ends over there, you can't keep anything inside of that fence because there is no inside. It doesn't close up. Does that make sense? Is everybody on board with that idea? Okay. All right. So again, the diagram helps us think that through anyway. Now, what's the conclusion and so what? Well, the fact that there is no surface means I can't even talk about that flux integral. There is no surface over which to even define this flux integral. And so the idea that I would compute my line integral in question with Stokes' curl theorem, which would have to be a flux over a surface that is an anti-boundary, yeah, it's not possible. So we know not to even bother thinking about Stokes' curl theorem as well. All right, is everybody on board? So again, we look back at this question. All I did here is I identified where I was on the diagram. I guess I stopped documenting up here. But I found my context. Oh, I want to be in highlighter mode. I found my context. I computed the appropriate operator and boundary. I've inferred my consequences. And what I see is, definitely don't even talk about Gauss, right? Or any related ideas. Stokes' theorem is not going to work. Now, if you do, make an attempt or something at Stokes' theorem, okay, well, at least that had a chance. That's not an outrage, such as computing divergence. That's an outrage, right? But if you're computing, we did compute the curl. It's not unreasonable. That had a chance of working. But the big conclusion is that we have one of our theorems on the table, ready to go. It will work. It's just a matter of doing it. And as it turns out, and I encourage you to work this out for yourself, indeed, that's the best way to solve this problem. This is a fundamental theorem of line integrals problem. And all you have to do, and I'm going to leave the details to y'all, but because we've done these before, and my focus right now is to talk about diagnosis. Find an antigradient and compute f of the end point minus f of the start point. Walk away. Everybody good? Okay. All right, let's look at our next example. Another line integral. Vector field, curve, compute the line integral, right? Now notice again, a lot of the same stuff applies. We're clearly in 3 dimensions. You can just count coordinates there. This is a 3-dimensional parametric curve. This is a 3-dimensional vector field. So we're in R3. So again, no Green's operator. Right? That's an R2 thing. We're in R3. Okay, let's see here. Next, well, let's go back to the diagram. Let me clean all this up. We're looking at a line integral in R3. We have a curve, we have a vector field. We're going to draw the same conclusions. The diagram tells me I should compute the curl, see what I get. The diagram says I should think about the boundary, see what I get. And so let's do that. Okay, let's start by computing the curl. Again, I'll spare us the tedium here. Actually, this one's not particularly tedious. The curl is going to be 0 again, as it turns out. By the way, not only is the curl 0, but furthermore, these 6 different partial derivatives you have to compute here to get to the curl, all 6 of those partial derivatives individually are also 0. So this is a super easy computation. You just, again, have to make sure you know the formula for curl and that you lay it out correctly. And don't forget that sneaky little minus sign that a lot of people forget. Okay, so back to the diagram. Whoops, wrong color. We indeed get 0. Okay, next, apparently we should be looking at the boundary points of this curve. So again, I plug in t equals 0, I plug in t equals 1, arithmetic ensues, and if I remember correctly, this curve starts at 0, 1, 1, and then ends at, well, 0, 1, 1. This curve starts and ends at the same point. I don't know exactly what this thing looks like. Look at this preposterous parametric curve. I don't know how to draw that. Maybe I could put something together if I really thought about it, but that's a weird parametric curve, right? So it doesn't really matter the details, though. The point is it starts there, and then it goes around and is weird for a while, and then it ends at exactly the same point. And that means, and you can see it right here in the picture, there must be some surface in between, you might say, whose boundary is that curve. So we have what I like to call an anti-boundary. And again, going back to the diagram, there is a, with the colors, the boundary was nothing, and so there is an anti-boundary. And by the way, I forgot to document on here when we were looking at the curl, but we computed the curl, we got 0, and that means that there is an anti-gradient. All right, so everybody with me so far? And I'm just, again, following the instructions. I'm letting the diagram be my guide. I'm doing what I'm told, right? And now I get some nice conclusions. And I hardly even have to write down details here. One thing I can see right away is that, Stokes' curl theorem's on the table. Because I was asked to compute a line integral over my original curve of my original vector field, and so instead, by Stokes' theorem, I can compute the flux through my new anti-boundary surface, whatever that is. I don't know what it is, but I know it exists, of the curl, which I know is 0. So here's the really nice little sweet punchline. I don't even really need to know what that surface is in this case, because on that surface, I'm looking at the flux of 0, and 0's flux is always 0. So I already know the answer to this question, 0. And now you got to write that down, right? You do have to actually apply Stokes' theorem and, make sure your reasoning flows on the page, right? Make sure that the grader can infer, okay, exactly what you're thinking and what you're doing. But Stokes' theorem, totally fine. On the table, that's one of your options. Okay, now, on the other hand, do we have any other options here? Well, again, we've got this groundwork laid. I know that there is an antigradient. And so that means that the fundamental theorem of line integrals is on the table. I was asked to compute that. I can instead compute this. I can find that antigradient, plug in the boundary points that I already have, and subtract. And what am I going to get? Well, I've already found that these two boundary points are the same. Start, end, same point. And so when I do that, when I plug into the, wrong button. When I plug into this formula here, f of endpoint minus f of starting point, well, these are the same point. And so I'm subtracting something from itself. Of course, I'm going to get 0. So take your pick as to which argument you want to write down. It's all good. But the point is the diagram has told us what our options are, and then we just get to decide where to take it from there. How you doing? Okay. All righty. Let's see here, back up to this. Oh, but just for the record, not that we're short of methods to apply here. So, I mean, we don't really need to make this observation, but just because we can, I did compute the curl was 0. Knowing that the curl is 0, yes, that tells me there's an antigradient. It also tells me path independence. Right? So I know that the curve that I was given, well, I can find any other curve that has the same boundary points and compute the line integral over that other curve. And so feel free to, if you want to, look at the starting point and ending point and parameterize. Now, that'd be silly in this case, right? A parametric curve that goes from here to here never moves. But if you want to take that point of view, that point of view is valid. Right? So another option. I don't think it's a very good one, but it's on the table. Okay, moving along. Okay, what do we got here? Again with the line integral. Again, 3 coordinates. Again, we're in 3 dimensions. So again, now Jack, I better clean up the mess here. Let's get rid of all of this. Again, we're computing a line integral. That means that we were given a vector field, we were given a curve, and again, follow the instructions. We're going to think about the boundary of that curve. We're going to compute the curl of that vector field. Let's see what we get. Okay. Compute the curl here. And what color did I use for that? I used orange. Okay. So the curl. Okay, you got to think through okay, so we get -1, -1, and -1. That's what I got anyway. Check me on that. Make sure I'm right. I am fallible, highly fallible, right? By the way, do be careful of one thing. This minus sign, as I've discussed, a lot of people get that minus sign wrong. Of course, keep in mind when you're computing curl, it's a symbolic cross product. Cross products are symbolic determinants. So there is the structure of determinant is in here, and determinant has that plus minus plus thing, and a lot of students forget that little minus sign. So heads up, do think about that very carefully. Try to be, touchy, paranoid about accidentally forgetting that minus sign, and that'll cut down on oopses. Anyway, there's my curl. What does that tell me? The curl is not 0. Okay, well, that means if I didn't get 0, that means there is no antigradient. That means the fundamental theorem is out of the question. Don't even waste your time. Don't try to find an anti-gradient. There is no anti-gradient. Does that make sense to everybody? Alrighty, let's think about the boundary. Looking at this curve here, this is not given parametrized. So we're going to take unavoidably a different point of view on how we're going to compute this. We're going to have to understand this curve, and then, having understood it, try to figure out where it starts and ends. All right, so we have to draw a picture here, and let's see here. I'm going to note that we have here a cylinder. Right, that's a cylinder. And then this is a plane. So I'm looking at how some plane intersects that cylinder. And I appeal to your geometric intuition, and we don't have to get the details exactly right in drawing the picture. But angled planes cutting through cylinders, they cut out ellipses. There you go. Is that cool? We can worry about the orientations later if we need to. For the moment, I'm just going to observe that it's this curve right here. Okay, good news. It's a closed curve. It doesn't start anywhere. It doesn't end anywhere. Right? Or I suppose you could say that you could pick a point and call that the starting point, such as if you were to parameterize it. But then, of course, you're going to end at the same point. So starting and ending at the same point is effectively saying that it never starts and never ends. Point of view. Okay, so back to the diagram. We in fact have zero boundary. That means there is an anti-boundary surface whose boundary is that curve. By the way, you can see what that anti-boundary surface is, at least in the picture, right? It's color choices. I'll use green, I guess. It's this. Highlighter. It's at least our easiest plane to choose would be that green, solid ellipse, if you will, kind of inside there. So there's the surface that we could conceivably play with. So back to the diagram. I computed the curl. Let's see here. I computed the curl. I have an anti-boundary surface. I even have a picture of it, and I could compute that flux. And so on the table, perfectly legitimate option to think about is, instead of computing the line integral as given, Stokes' theorem tells me that I could instead compute this flux. Right? I can compute the flux of my newly identified anti-boundary surface of the curl vector field that I just computed. Now again, of course, that's exactly what Stokes' theorem says right down here in the algebra, but I kind of like the way it just leaps off the page at you in the diagram. Okay. All right, so we have an option, and that's a perfectly reasonable option, and you might ought to entertain doing that option. I will point out one last thing here, though, and that is that sometimes, even when the original line integral in this case can be transformed into another option, that doesn't mean that it will help, right? When I do this, when I take my given line integral and rewrite it as a flux integral, is it better? Does that help me, right? I mean, if I'm going to compute a flux, whoopsie, I keep hitting the wrong button. If I'm going to compute a flux, I would then have to either parameterize this surface. Not that that's hard. It's in an easily identifiable plane. I could solve for z. I could use the graph parameterization. It's not that bad to parameterize this surface, right? But if I use the graph parameterization, the domain for the integral would be a disk, and that means now I'm using polar coordinates. There could be some work down that road, right? So what I want you all to also always remember is that always on the table, always an option, is to just compute what you were asked to compute directly. Brute force. Right? So if I were to compute the line integral as given, what I would have to do, forget about all this business about a surface. I just need to parameterize that curve. Pretty easy to parameterize. I can see x and y are going to be cosine and sine. I can solve for z in terms of x and y. That means z is minus cosine minus sine, right? I mean, you just write it down what z is once you know x and y. And so it's not hard to parameterize this curve. The vector field's not that bad. It might just be easier just to crank this one out directly. And I think that's a nice sort of, do both sides and see what you get. Compute on the one hand, just because you can, compute the original line integral over the original curve, your original vector field, right? See what you get, see how that works. But then also take the flux through your new surface S of your curl vector field dot ds, again, by parameterizing the surface. See what that gives you. Right? And then just compare which one was more work. Right? These are healthy calculation. Anyway, so again, you've got options. What do you think? Everybody happy? Okay. Next option. Excuse me, next example. Okay, so again, 3 dimensions. Again, line integrals. So we're doing a lot of stuff in kind of the same area. A lot of interesting ideas kind of come together there. So a lot of this goes down the same as what we've already seen. Let me get rid of all of this. We have a line integral to compute. We have a vector field given. We have a curve given. We're going to compute the curl, see what we get. We're going to look at the boundary points, see what we get. And then we're going to decide, okay, so let's compute the curl. We've already computed this curl. This is literally this exact same vector field from the last question. So we already know the curl. The curl is equals negative 1, negative 1, negative 1. Not 0. With the colors. Not 0, no anti-gradient. Forget about the fundamental theorem. Never going to happen. Right? Let's see here. Let's look at the curve. The curve here. Okay. Well, oh gosh. Again, I have a cylinder intersecting a plane. Something very lucky is going to happen here, though. My cylinder. My plane, x minus z equals 0. Oh gosh, these are hard to... this is not a good picture of that plane, but anyway. The curve is the intersection of those two. I'm drawing morally the same picture here. So again, closed curve. Again, that means there's a new surface. Right? So we have found now this new surface. Oh, with the colors. We have found a new surface whose boundary is our original curve. Right? So Stokes' theorem is on the table. I can compute the given line integral instead as a flux. This is all exactly like that last question. So again, sort of take your pick. But one thing has changed meaningfully, right? And this is why I say you should always head on a swivel, always looking to get lucky, always looking for that one little detail that makes everything go perfectly. Let's think about the surface. This surface right here. I can write down that normal vector pretty easily. Because that normal vector comes out of this plane, x minus z equals 0. And there's a orientation issue to worry about, right? Counterclockwise as seen from above, so it's oriented, kind of like so. And we worry about that if we need to. But what I can say immediately is that plus or minus, depending on the orientation, but this normal vector points in the direction of 1, 0, negative 1. So I'm just going to write down 1, 0, negative 1. And, of course, I might be going the wrong direction, but the plus minus handles that. And, of course, don't forget it's got to be a unit vector, so I am going to divide by the square root of 2. Okay, and I claim that this is a massive win here. This is super useful information. And why? What is it that this does for me? Well, again, let's go back to the diagram. The diagram tells me that I should look at my curl and my new surface and compute my flux. I keep hitting the wrong button. So I'm going to write down Stokes' theorem here. Stokes' theorem says that is a flux through my new surface S of my curl dot ds. Okay, now wait a minute. We know how to write the ds vector. The ds vector, the ds vector is our normal. Let's see here. So, plus minus, something we got to worry about. But 1, 0, negative 1, got to normalize square root of 2, and then ds. So here would be my Stokes' theorem calculation. You could still parameterize that curve. You could still compute this the old-fashioned way. But notice how little effort it took me to write this down. The normal vector, practically a free gimme. I mean, details to be determined, right? But a lot of the information about the normal vector I just observed basically for free. Curl, I had to compute a few partials, but I had to do that anyway. This integral is obviously 0 because the dot product is 0, and we're done. Right, so this is a really good thing to be heads up about, right? So, you want to look, these little details can matter. So look at it, for example, if there is a plane whose equation you have that's clearly going to tell the story about your new surface. Think about, hey, did we get lucky with the normal vector? Right? And as always, let the diagram be your guide as to what would I do with the normal vector in the first place? Well, that's going to be part of my flux computation, and so it is, according to the diagram, the curl field that I would need to relate it to in this dot product. So, again, I feel like the diagram, is guiding us toward a reasonable diagnosis of the questions. Okay, a couple minutes left. Let's talk about these last ones. Let's see here. So here we have, different. Now a flux. Right, so this is a different question. This is a flux calculation. Let's go back to the diagram and sort of re-center ourselves here. We're looking at a flux now, which means that whatever vector field that we were given, we're going to need to think about its divergence. Whatever surface we were given, we're going to have to think about its boundary curve. Right? So, okay, fine. Let's go back to the thing here. We'll take our vector field and we'll compute the curl. The curl here. What I did. Why did I say compute the curl? That doesn't make any sense. I wasn't following my own rules, was I? It says right here, diagram tells me I should be looking at the divergence. I think I just had kind of a, I've been computing curl a lot. for the last few examples. So anyway, follow the diagram. Keep yourself honest. We're computing the divergence. My bad. So the divergence here is 0, as it turns out. Which means, because I get 0, that means there is an anti-curl. Bad news. Just because there is an anti-curl just because there is an anti-curl doesn't mean that I know how to compute an anti-curl. So very often when you find yourself in this situation that, hey, there's an anti-curl. Yeah, very often it's just not that useful because you don't know how to find the anti-curl anyway. But in this case, check it out. We are given the anti-curl. It's this thing right here. And it says so right here in the statement of the question. This vector field 0, 0, xyz, its curl is f. Namely, this is the anti-curl of f. So you could, on this question, take the given flux by way of Stokes' curl theorem. You can rewrite that as this line integral. The anti-curl is given. The curve is something you can infer just by looking at your surface and thinking about its boundary. That's a perfectly reasonable, good way to solve this problem. And it looks like I'm out of time, so let me just throw one very, very last little quick thing. Also, because it's a curl, surface independence. Also on the table, and I encourage you again to work out both of these. Work this out with the curl theorem, work this out with surface independence, see what you get, see which one you like better. They both work great. Okay, see y'all later. Have a good one. Yeah, see ya.